Hello friends, I welcome you in lecture number 37 on group theory. In this lecture we will discuss two problems on group theory which were asked in GTU previous year exams. So first question is, suppose we are given some group denoted by G with respect to binary operation denoted by star. Then we have to prove that inverse of A star B equals B inverse star A inverse for any AB belongs to G. If we take any two elements denoted by A and B in any group G with some binary operation star, then this property is always true. That is, inverse of A star B equal to inverse of B star inverse of A. Some authors are ignoring this star operation and they can write this same thing in this way also. Inverse of AB equal to B inverse times A inverse. So sometimes they can ask you in this way also. Here it is understood that we have arbitrary operation star in a group G. So some authors are not writing star operation. Instead of that they are writing in this way. So the same question can be asked in this way also in different notations. Now what we have to prove is that inverse of this element AB is equal to B inverse times A inverse. Now if you recall the definition of inverse in a group, then we know that if we have two elements, say X and Y, and suppose E is the identity of group G, then X and Y are called inverses of each other if X star Y equal to Y star X equal to identity element. If this happens, then we say that X and Y are inverses of each other. Here you can see that we have to prove that inverse of A star B is B inverse star A inverse. So suppose we consider X equal to AB and Y equal to B inverse times A inverse, then we have to prove that inverse of X, because I am considering AB equal to X, I have to show that inverse of X is equal to B inverse times A inverse. So for that we have to prove that X star Y, instead of X I will write AB. So I have to prove that AB star, what is Y? Y is B inverse A inverse, that is equal to B inverse A inverse, that is Y star X equal to identity element. If I can prove this, then I have shown that inverse of AB is nothing but B inverse into A inverse. Now here they have used this star notation, so we will also use star notation to answer this question. If they are not using star notation, then we can also ignore star notation. So whatever instructions or notations are used in our question, we will use those notations to answer the question. If they ask in this way, then we will not write here A star B, we can simply write AB also. But here they have asked to show that inverse of A star B is B inverse star A inverse. So we can consider, for simplicity, suppose I consider X equal to A star B and Y equal to B inverse star A inverse. Then you can see if I take A star B equal to X, then here I will have X and this I denote by Y. So I have to prove that inverse of X is equal to Y. So that we are writing. So to prove that inverse of X is equal to Y, this we have to prove. Now by definition, if we recall the definition of inverse, by definition X has inverse Y if X star Y equal to Y star X equal to identity element where this E belongs to G is identity of group G. So this I have to prove. So now I start by considering this x star y. First I will show that x star y equal to identity element. What is x? X is a star b. So here I write a star b, and y is y equal to b inverse star a inverse. So let me take y equal to b inverse star a inverse. Now because G is a group, this operation is associative, so I can interchange these brackets because these are the elements of a group, so I can apply associative property. So in the bracket we can mention that using associative property of a group or associative property of a binary operation star, because G is a group. So this step is using associative property. And now we want to prove that x star y equal to identity element, and here we can see that B is an element of G and G is a group, therefore B star B inverse is identity, and this is A inverse. So what we have used here, B star B inverse equal to E, because B is an element of a group, and because E is the identity, we can write A star E equal to A, because E is the identity of the group. So here we are using the fact that A star E equal to A, and this is because this element E is identity, and because A and A inverse are inverses of each other, this is equal to E. So what we have shown, x star y equal to E, therefore x star y equal to E. Similarly we can show that y star x equal to E. Suppose we consider y star x. What is y? Y is B inverse star A inverse star x is A star B. So here we will use associative property and we will combine these two, A inverse star A star B, again using associative property of a group. G is a group and all these are elements of G. Now A and A inverse are inverses of each other, so I can replace this by identity element, and if I consider identity element with element B, then I get B. Okay, that is by definition of identity element, and by definition of inverse this is equal to identity. Therefore we have shown that y star x is also equal to identity, and here I have x star y equal to identity. This I can give number 1, this is number 2, y star x is identity, and if we combine number 1 and 2, from 1 and 2, x star y equal to y star x equal to identity. This means inverse of x is y, and we have taken x equal to A star B, so I replace x by A star B, and y was taken as B inverse star A inverse. So if we have a group G, then we can always say that inverse of A star B is equal to B inverse star A inverse, that is AB inverse equal to B inverse times A inverse. So this is the first question, very easy question asked in GTU Winter 2023 exam. They have asked another question also in this same exam, and it was asked that if you have this property in your group, if in your group G with star, for any two elements, if A star B square equal to A square star B square, then that group G is always abelian. If square of A star B equal to A square star B square for any two elements in a group G, then that group G is abelian group. This was asked in GTU Winter 2023 exam. Now what about converse of this? That is, if this property is satisfied, then G is abelian. And converse of this is, if G is abelian, then can we say that it implies that A star B whole square equal to A square star B square. So converse is also true. Here they have asked this question in this way, that if this property is satisfied, then G is abelian. But converse of this result is, if G is abelian, then also this property is satisfied. So we have two statements here. That one statement is G is abelian, and another statement is square of A star B equal to A square star B square. And here they have asked in this direction, that if this is true, then prove that G must be abelian. And reverse implication is also true. That is, if G is abelian, then this property is satisfied. So we are going to prove both the directions. They can ask you to prove this result in both the directions also. Here they have asked in one direction only. That is, if this property is satisfied, then G is abelian. So this is another nice property of abelian group. We know that our group is abelian if for any two elements A and B in a group G, A star B equal to B star A. If this property is satisfied, then we say that group is abelian. This is the definition of abelian group. And now from this result we have another property, that is, if square of A star B equal to A square star B square, then also our group is abelian. And it is double implication, that is, if G is abelian group, this property is satisfied, and if this property is satisfied, then G is abelian group. So here I am proving in both the directions. First I will assume that group G is abelian and I will prove this property. Then I will assume that this property is satisfied and I will prove that G is abelian. First we are assuming that suppose G with binary operation star is abelian group, and we want to prove this property. So what we have to prove here? To prove that square of A star B equal to A square star B square for any two elements A and B in a group G. So proof is easy. We can start by considering any two elements. For any AB belongs to G, we start with left hand side. We want to show that A star B square equal to A square star B square. So we start from left hand side. This I can rewrite as A star B star A star B, because I have square here. Now because G is a group, I can interchange these brackets using associative property. I can rewrite in this way. So this is using associative property. Because G is a group, associative property is satisfied. Now because G is abelian, I can rewrite B star A equal to A star B. So here I am using our assumption. We have assumed that group G is abelian. Therefore A star B equal to B star A for any two elements of G. So that I am using here. I am replacing B star A by A star B. Now I am using associative property again. I will consider this A with this A and this B with last B. So I am rewriting using associative property again. So here I have mentioned whatever I am using associative property. And this A star A can be rewritten as A square and this can be rewritten as B square. And this A and B are arbitrary. Therefore we have shown that if G is an abelian group, then for any two elements of G, this property is satisfied, that is square of A star B equal to A square star B square. Now we consider converse, that is we assume that this property is satisfied for any two elements. Suppose that for any two elements A, B in a group G, we have this property satisfied, that is A star B square equal to A square star B square. And we want to prove that our group G is abelian. If this property is satisfied, then G with star is an abelian group, or we can simply write that to prove that G with star is abelian. That is what I have to prove. I have to prove that if I take any two elements, then I have to show that A star B and B star A are equal. So for that I am taking any two elements. We start by considering A and B in a group G, and I want to prove that A star B equal to B star A. Now what is given? If we have any two elements in a group G, then this property is satisfied. So we start by this property. First step is we are writing whatever we have assumed. We have assumed that if we take any two elements in G, then we have assumed that square of A star B equal to A square star B square, and we want to prove that A star B equal to B star A. This we want to prove. So that we will prove from this equality only. So now what I am doing, I am writing this A star B as A star B star A star B. On right hand side I am writing A square as A star A, and B square can also be written as B star B. So we are rewriting all these things. Now I want to prove that A star B equal to B star A. So you can see here I have B star A and here I have A star B. So first, using associative property, I will combine B star A on left hand side. Here I am combining B star A, and here using associative property I combine A star B. So what I am using here, using associative property. Now I want to prove that B star A and A star B are equal. So I don't require A here also, and I don't require B on right hand side of both the sides also. So what we can do here, we can multiply left sides of both the sides, or we can multiply left sides by inverse of A, and this right sides can be multiplied by B inverse. If I multiply this by A inverse, I will have A inverse star A, that will give me identity. If I multiply this by B inverse, I will have B star B inverse, so that will give me identity, and we will be able to prove that B star A and A star B are equal. So in the next step, on the left side we multiply by A inverse. So here I write A inverse star A and I combine it with A star this B star A as it is, and here I multiply by B inverse on right side. So to the left we multiply by A inverse, to the right we multiply by B inverse, and same thing for right hand side. Here also we multiply by A inverse, so A inverse star A, and we keep this A star B as it is. A star B star, this is multiplied by B inverse, and this we can always do because A and B are elements of group G, therefore their inverses exist. Now by the definition of inverse, this is identity element. Suppose E is the identity of group G and this is also identity element. Same thing here, E star A star B and B star B inverse is identity element. Now we know that if we consider identity with this, we will have B star A. We can write one more step, and same thing here, this is A star B star identity, that is A star B star E, and again using the definition of identity, we have B star A star E equal to B star A, and here we have A star B star E equal to A star B. So we have proved that A star B equal to B star A, and this A and B are arbitrary elements of given group G. Therefore G is an abelian group. So therefore G with star is an abelian group. So in the converse part, we assume that if this property is satisfied, then G is abelian, and in the first part we assume that G is abelian and this property is satisfied. They have asked this part, converse part, in GTU exam, but they can ask this result in both the directions also. So, and it is very easy to prove this result. So they have asked in this way that if this property is satisfied, then prove that G must be abelian, but they can ask if and only if also. Here they have asked in one direction only. So what we have proved in this lecture is, if G is any group, then inverse of A star B is equal to B inverse star A inverse, and if this property is satisfied, second result, if A star B square equal to A square star B square for all elements in a group G, then G is abelian, and if G is abelian, this property is satisfied. So these two are very nice results of group, and they are very easy to prove as we have done in this session. So this is all about this session. I hope you like it. Thanks for watching.